So we were doing the following problem, okay? So consider flow between two horizontal infinite parallel plates. So whenever they tell you that the plates are infinite, okay? This means that along these directions, you don't have constraints for the flow. So here you have a rectangular plate that is infinite in dimensions. So when your flow will move, it will not have any constraint along these two directions. This is why, okay, along this one, because we said that we have along this direction it's infinite, and along this one is infinite. So the flow will only be constrained along y direction, okay? And as we mentioned then, the velocity will be only along x in this case, okay? So your flow will move along x direction. Now, by just saying that I have this flow between this infinite parallel plates, and the flow is parallel to these plates, now I can say that if I apply first the continuity equation, so keep in mind always, whenever you have such problem, to write the continuity equation and Navier-Stokes equation, okay? So if we write the continuity, if you remember, we are dealing here with an incompressible flow and with a Newtonian flow. So mu is constant. This is why mu and rho are constants. This is why I can apply Navier-Stokes equations. And also from continuity, what can I write? In Cartesian coordinates, I can write del u by del x plus del v by del y plus del w by del z equals to 0, okay? But we said, since our flow is moving between parallel plates, and these parallel plates are infinite, so our flow will move in a way parallel to these plates, and it will not have any constraint along to bounded along z. Also along x, it will not have any constraint. So my flow will only vary with what? And because this is because along y, due to non-slip condition, it is forced to have 0 velocities at the walls, and it will increase as we go far from walls. This will give us a parabolic profile, as we'll demonstrate together, okay? So now, since our flow is known to be parallel to the plates, so it's along x-axis, v and w are 0. So we can deduce from the continuity equation, and this was expected, that why it was expected, because we don't have any constraint along x, okay? So del u by del x is then 0. This means that u is not varying with x. And already along z, we have infinite plate, as we said, infinite dimension. So also it will not vary with z. Therefore, our velocity u will only vary with y, okay? So first, we can write that we have only u, and this u is a function of what, okay? So now we can proceed, okay? The next step will be to write the Navier-Stokes equation and apply them on this particular case. So if we go back to our equations in Cartesian coordinates that we developed, these are Navier-Stokes equations. Yes? Yes.
Hassan is in the waiting room. Can you please let him in?
Yes, yes, sure. Yeah. Okay. So now, going back to these equations, let us solve for the given problem. First, it's a steady state problem. So all terms del by del t will cancel out. Now, we said that u is not only varying with y, so del u by del x is 0. And here v is 0, so this term will cancel out, and w is 0, so this term will cancel out. Now, in this problem, y is the vertical direction, so g vector is only along y, so we just have gy equals to minus g, and therefore gx is 0. And now also we said that u is only function of y, so the second derivative of u with respect to x is 0, and the second derivative of u with respect to z is also 0. Okay, so we end up now with the following result, that from the first equation we get minus 1 over rho del p by del x plus del square u by del y square equals to 0. This is equation number 1. Now we move to simplify the second Navier-Stokes equation along y. Steady application, so del v by del t is 0. V is 0, so this term cancel out, and this one also, and this one also. Concerning gy, it's minus g, and minus 1 over rho del p by del y. Now for v is 0, so all of these terms will cancel out. So the second equation will just give us that 0 is equal to minus 1 over rho del p by del y minus g. Okay. Now the third relation, also steady, del w by del t 0. W is 0, all of these terms will cancel out. Gz is 0, w is 0. So the last equation will give us that minus 1 over rho del p by del z is 0. Okay. Let us now write these three relations and try to make the conclusions about the pressure and velocity. So these are the three equations after simplification of the Navier-Stokes equations. Okay. Now, if we take first the last relation will tell us that P is independent of Z. Okay. So from equation 3 here, we can say P is only a function of X and Y, and is not varying with Z. This is the first conclusion we can make. Now, if we go to the second equation, from the second equation, we can say that del P by del Y equals to rho G minus rho G. Okay? So now, if I integrate with respect to Y, then I can write that P is equal to minus rho G Y plus a certain function of X. Okay? So until now, and we are sure that we don't have Z because from the last relation, P is independent of Z. Now, going to the first equation, okay, we can write the following. We can write that, look, from the first relation, what do you have? You have that del P by del X, okay, is equal to mu times the second derivative of u with respect to y. Okay. Now, if I use the expression of P developed here, I got that P is minus rho gy plus fx. So if I derive with respect to x del P by del x, what do I get? I get first, since this is a function of y, the derivative with respect to x is 0. Okay. And I just have then del f by del x. Okay, where f is only a function of x. So if I look at these two expressions, I will obtain something that is in contradiction with each other. Why? Because here in this equation, del p by del x is the second derivative of u with respect to y, and u is only function of y. This means, okay, that del p by del x is function of y. And from the other relation, I have that del p by del x is the derivative of a function that is only function of x. This means that del p by del x is function of x. So what is the only possibility that satisfies these two conditions? So can I have at the same time a function only function of x or only function of y? What should be the solution here? What should be del p by del x? It should be a constant, okay? Because if del p by del x is a constant, this will be solved. Since if I have a function of y, when I derive, I can get a constant. And if I have a function of x and I derive, I can get a function of, I can get a constant. So to have this, f should be then, so here, the condition is del f by del x is a constant. So f should be a linear function of x. And also mu times second derivative of u with respect to y should be a constant. And then u should be a second degree function of y. This is why I told you the flow profile is a second degree parabola, because we have demonstrated together here that the second derivative of u with respect to y is a constant. And this means that u is a second degree function with respect to y. Okay? Any question on this? So now, once I am sure that my del p by del x is a constant, this will simplify things a lot. Okay? Because now I can integrate this relation to get the velocity profile u, function of the pressure gradient with respect to x. Okay? Since del p by del x is a constant, then to calculate it, I just have to know the pressure at 2 points of my flow. So for example, if this is point 1 and this is point 2, if I know the distance between these 2 points, okay, then if the distance is L, then I can say that del P by del X is equal to P2 minus P1 over L. Okay. Now, if you remember, we talked sometimes about what is driving the flow. And we said to drive this flow, we need a pressure gradient. And P at 1 will be larger than P at 2. So this will be a negative result. Okay. Del P by del X will be negative. This is why we say, we call it, if you want, minus delta P. We consider delta P is an absolute value, and delta P represents the pressure drop. So if we consider the pressure drop to be equal to delta P, then del P by del X will be between 2 points is delta P over X. Okay? So only I need to know pressure at 2 points to be able to determine this constant del P by del X. Okay? Now, once I know del P by del X, to get u, all I have to do is to do double integration. So I integrate 2 times. So first, 1 second. Okay. So if I do the first integration, I'll get the following. We have that the second derivative. Why we are writing d not del? Because u is only function of y. So you can represent del symbol by d. So you can say that the second derivative of u with respect to y is equal to, if you take mu to the other side, is equal to 1 over mu times del P by del X. And as we said, del P by del X is a constant. So now, since it's a constant, when you integrate, you will get this constant times y plus C1, plus constant C1. And to get C1, we'll use a boundary condition. Okay? Now, if I integrate a second time this relation, I will get 1 over 2 mu del P by del X times y squared plus C1y plus C2. So now, to be able to define completely my profile, I need to get the constant C1 and C2. So I need two boundary conditions to get C1 and C2. Okay? Here, to get them, all I have to do is to say that if you look at your flow, we know that due to non-slip condition, okay, at y equal to minus h, which is corresponding to the bottom plate, the velocity u is 0. And also we know that for the upper plate, okay, at y equal plus h, also u is 0. This will give me two equations, which will allow me to get the value of C1 and C2. Okay? Also, another possibility will be to use the symmetry condition. Because you have symmetrical flow, you will be sure that the maximum will be at the center line. So another boundary that is possible to write is that at y equals 0, del u by del y is 0. Okay? So you can choose any two of these three conditions to get your C1, C2. So for example, if we consider the condition at the center, that del u by del y is 0 at the center. So when y equal to 0, del u by del y should be 0. We end up with C1 equal to 0. Okay. Now, second step, to get C2, we apply for y equal to h. So we replace y by h. We get here 1 over 2 mu del p by del x h squared plus C2 equals to 0. Okay. So we end up with C2 equal to minus 1 over 2 mu del p by del x times h squared. Okay. And then this will give you that the velocity distribution is of the following form. In case of flow between two fixed infinite plates, the profile of velocity is parabolic shape and is given by 1 over 2 mu times del p by del x times y squared minus h squared. Okay. Now, once we know the velocity profile, okay, we can find the flow rate, we can find several properties related to the flow. We can find the average velocity, etc. Okay. So now, if you want to calculate the flow rate per unit depth, so if I consider a depth per unit depth, so for a depth of 1, okay, for a depth of 1, what will be my cross-sectional area? Look, my area is a rectangle, okay, but here it's of infinite dimensions. This is why I will define the flow per unit depth. So for a depth of 1, if I consider a depth of 1, okay, and my velocity profile is varying with y. To get Q, I should perform integration to get my volumetric flow rate because the velocity is varying with y. Okay. Since my velocity is varying with y, I will have to do an integral procedure to get my total flow rate. So it's equal to integral between minus h, which corresponds to the bottom plate, to plus h of UDA. Now, what is the elementary area I will consider here? I will consider an area of unit depth and of thickness dy, because my velocity is varying along y, so I will take a very small thickness along y, and then dA is 1 times dy, so I can replace it by dy. And now all I have to do is to integrate this function, okay? You have that this is a constant, so you can take it outside of the integration. And the integral of this term is y cubed over 3 minus h squared times y, because h squared is a constant. And you will apply it between the boundaries minus h and h. And by performing your calculation, you will get the following flow rate. This is the value of your flow rate. Okay. So now we got Q, the value, the corresponding expression of Q. Okay. Now we said that the pressure gradient del P by del X is negative because this is the driving for the flow. So to be able to have a flow in this direction, I should, if you want, give a certain potential. This potential to move is due to creating a pressure drop, because fluid particles will tend to go from high pressure to low pressure. So if I ensure between 2 points a decrease in pressure, the particles of the fluid will tend to go from high pressure to low pressure. And this is what we demonstrated together, because if del P by del X is 0, no flow, okay? So this is what will drive motion, the presence here of pressure variation. Of course, this is the case because my motion is horizontal. But if you have motion in the vertical direction, for example, your flow will not only move under the effect of pressure, but also under the effect of gravity, okay? But here, the flow is horizontal. So what is driving it in this case is the pressure gradient, okay? Now, as we said, we can say that we can define the pressure drop between 2 points delta P. And then delta P over L can be written as minus del P by del X. As I told you, delta P is an absolute value. It's a pressure drop, so it's positive. This is why I will put minus del P by del X. So now if I replace del P by del X in this equation by minus delta P over L, and I already have minus before, okay, then I will get that Q is 2h cubed times delta P over 3 mu times. So as you can see, the flow rate Q is proportional to the pressure drop. Higher the pressure drop, higher the flow velocity, higher the flow rate. And of course, it's proportional to the thickness separating the two plates, because larger h will correspond to larger area. And it's inversely proportional to the length L between the 2 points, because if you increase L for same delta P, this means that you have a lower pressure drop over a lower pressure gradient, sorry, and pressure gradient is the driving for your flow, okay? And viscous effects will try to resist flow motion. This is why viscosity is inversely proportional to it, okay? Now, what about the mean velocity? The mean velocity or average velocity can be calculated as the flow rate, so V average, and sometimes we symbol this by V with a bar, or just big V, okay? By putting just big V, it means we are taking here the average velocity. Big V is defined as the flow rate over the corresponding area. And we said here the flow is defined per unit width. So A is 1, which is the width, times the height. And the height here is 2h for the case we are considering. So we can say that the average velocity is q, which is flow rate per unit depth, over 2h. So now if you divide here q by 2h, you will get the expression of your average velocity. You have 2 will cancel out. H cube will become h square. So it's h square times delta p over 3 mu f. Okay. So this is the expression of the average velocity in this case. Okay. Now, how to get u maximum? We already have seen that the maximum takes place at y equals 0, midway. So to get u maximum, all you have to do is to replace y by 0 in the expression of velocity. And this will give you that the maximum velocity is h squared over 2 mu times del p by del x. And if we replace del p by del x by minus delta p over L, we'll get that u max is h squared over 2 mu. And as expected, of course, u max is larger than the average velocity. Okay, and now you can find the ratio of u max and the average velocity. So if you divide u max by v, u max over v will give you, you will see that you will get a number because all terms will simplify. So you have delta p, mu L, and mu L. So you end up with 3 over 2. Okay. So U max is 1.5 times V average in the case of flow between infinite parallel plates. Okay. And finally, what about the pressure variation? Okay. If you want to get an equation for the pressure variation, you should go back to the following, the relations that you have, that del P by del X is a constant. Okay. Del P by del X is constant. And we have seen together that the pressure P can be written as what? It's minus rho G Y plus a function of X. Okay. And when we derived this result, we said that del F by del X is just equal to del P by del X, which was demonstrated to be a constant. This allows us to get the expression of F. So if you want to get F function of X, all we have to do is to integrate. So we can replace del P by del X by minus delta P over L. And when we integrate this function with respect to X, it's times X plus a certain constant. Okay. So now, if you replace back F by its expression in the pressure relation, you will get that your pressure is minus rho Gy plus del P by del X, or minus delta P over L times X, plus a certain constant. How to get this constant? You need a boundary condition. Okay. So if they give you at X equals 0 and Y equals 0, the pressure is P0, then your constant should be equal to P0. Okay. So, and if you know the pressure at another location, you can get your constant. You can get the value of your constant, and this constant will correspond to the pressure at x0, y0, because when x is 0 and y is 0, the pressure will be equal to P0. Okay. Any question on this part? So this is the procedure to follow. We will study together different flow fields, different types of flows. And for each type, we'll repeat the same procedure. We'll apply the continuity equation, the Navier-Stokes equation. Then we will get the expression of the flow rate, of the velocity, average velocity, maximum velocity, and pressure field variation. Okay, in this way we can characterize analytically different types of flows. Another interesting example that is encountered a lot in fluid applications is Couette flow. Okay, this flow differs from the one that we have already studied just by a boundary condition. Because look, you still have infinite parallel plates, but instead of having both of them fixed, here you have the bottom plate that is fixed, while the upper plate is moving at a constant velocity. Okay, and you want now to derive equations for your velocity field and pressure field. So first, okay, when you reduce the Navier-Stokes, when you apply the Navier-Stokes equation and continuity equation, you'll still obtain same results because nothing has changed if you want in terms that the velocity is parallel to the plate. So it's only, you have only U, no V, no W, V0, W0. And also concerning, if you apply continuity, you will get that del U by del X equals 0. So U is only function of Y since Z is infinite. Okay. So until now, same conditions. Also, if you simplify Navier-Stokes, nothing has changed. The only thing that has changed is the boundary condition. So instead of saying that at y equal to here, they change the frame's origin because it is easier for the expression, but you can still take it at the center. As in the previous case, we took it at the center because we have symmetry about the center. Here, we don't have symmetry about the center because you don't have symmetrical condition. Here, velocity is 0, U is 0, while at the upper plate, small u is equal to big U. Okay, so the difference is that we should change boundary conditions, and here they selected the frame to be at the bottom plate, so we can write that in this case for y equal to 0, u is equal to 0, while the second condition for y equal to b, which is thickness between the two plates, u is equal to big U. So this will give us different constants, okay, and therefore different profile. So let us together find this profile. So first, as we said, the Navier-Stokes equation will end up with the same conclusions, that P is minus rho gy plus f1x, and du by dy is 1 over mu del P by del xy plus c1. And if we also can demonstrate that del P by del x is constant in the same way we did in the last example. So we can integrate to get u, and the equation will be as follows: u equals to 1 over 2 mu times del P by del x times y square plus C1y plus C2y. Now, how to get C1 and C2? We should apply these boundary conditions. So let us start with the first one. For y equals 0, u equals 0. So what will happen? Y0, sorry. So y0, u is equal to 0. So this will give us that what is C2? We can conclude then that the value of C2 is 0. Okay. So first here C2 is 0. Now we still have to get C1. So we can now write that u is equal to 1 over 2 mu times del P by del x times y square plus C1y because no C2. Okay. Now to get C1, we use the second condition, which is for y equal b, small u equals to big U. And now we replace small u is big U equals to 1 over 2 mu times del p by del x times b squared plus C1 times b. Okay. And then you can get your constant C1. And then when you plug C1 in your equation here, after some simplifications and taking common factors, you can come up with the following relation. That u over small u over big U is y over b minus b squared over 2 mu times big U times del p by del x times y over b factor 1 minus y over b. Okay. Now, this means what? Let us do some interpretation of this result. Okay. First, here, flow can be driven just by the moving plate. No need for a pressure gradient. You know why? Because look, if del P by del X is 0, so if you don't impose a pressure drop through your system, your flow will still move, but the variation of your velocity will be linear. Why? Because you are imposing motion at the upper plate. So your fluid is forced to move at the upper plate. So at the upper plate, U equal to big U. And at the lower plate, U is equal to 0. And if you don't have pressure variation, then this motion, okay, will lead to linear variation of your velocity profile, which will increase gradually from 0 to U. And if you remember, when we started fluids, we considered that we can assume linear profile in some cases. The reason was because we are not creating a pressure drop. So pressure is constant in this case. So only flow will move under the effect of the moving plate, and the variation of U will be then linear. Now, again, from this result, you can also deduce back the previous result. Because look, if big U is 0, if you don't impose motion on the upper plate, you will end up with the first relation we got before. Okay, that velocity will be due just to pressure gradient. Okay, and if you have both, if you have U and del P by del X, if you impose a certain pressure gradient, then the total velocity will be a combination of both. And here you have the possibility to have the pressure gradient here can be positive or negative. So if you have a pressure drop in this direction, this will increase the velocity in this direction. But if the pressure drop here is, if pressure is increasing as I'm moving in the flow direction, this will tend to slow motion. Okay, because an increase in pressure in this direction will tend to give a velocity for the flow in the opposite way. And then you will have one positive effect, one negative effect that will act against each other. And you can compute the total velocity, if it's positive or negative, from the combination of both effects by just doing calculation. Okay. Any question on this? Okay. So we'll open another meeting to continue.